Hello Professor, we are Group 2 and today we'll be presenting our project on the Winkler Foundation analysis using MATLAB. Here's an overview of our presentation. First, we'll introduce what is Winkler Foundation and MATLAB code overview, input variation and conditions. Next, different 2-column rows, 3-column rows, 5-column rows. We'll start with our first topic, the Winkler Foundation. The Winkler Foundation is a foundation design concept that models soil as a set of independent, linear, elastic springs, rather than treating the soil as one continuous medium. This model represents the ground using multiple independent springs. One of the main characteristics of the Winkler Foundation is that when external forces are applied, the deflection at each point is directly proportional to the load and the soil reacts at the specific point. In other words, if a load is applied at a certain point, the deflection at that point is calculated independently from neighboring springs. This is based on the key assumption that individual springs do not influence each other. The main characteristics of the Winkler Foundation that are summarized into 3 points. First, it's a simple and intuitive model, allowing quick and clear design by representing complex soil conditions with springs. Second, it effectively captures localized soil deformations, enabling precise independent analysis at specific points. Lastly, it's particularly useful for analyzing continuous and composite foundations, efficiently modeling soil reactions beneath these structures. This concludes my overview of the basic concept and characteristics at the Winkler Foundation. Next, we'll move on to discuss the MATLAB-based analysis method for the Winkler Foundation in detail. Thank you for listening.
Now I'll explain the technical structure of our MATLAB codes based on the Winkler Foundation model. This model simplifies the soil structure interaction by treating the foundation as a beam, supported by a series of independent linear springs. Each spring reacts only to the vertical displacement at its own location, which means no interaction between adjacent springs is considered. This allows us to model localized soil deformation in a straightforward way, which is especially useful for continuous or strip foundation. In our code, vertical point loads are applied to simulate column reactions, and they are spaced uniformly along the beam. The load value combine both dead loads and live loads, and all units are in found force. The beam itself is modeled as a one-dimensional element with discrete spring supports beneath it. The entire workflow is divided into 8 stages. It begins with defining geometry and material properties, then generating the spring layout and stiffness metrics. Next, loads are applied, the system of equations is assembled and solved, and internal forces are computed. Finally, the program visualizes results such as deflection, shear force, and bending moment. The modular structure makes the code easy to modify and apply to different design cases. Now let's look at the input setup. The user needs to define three main values. First, the flexure result EI, which controls how the beam resists bending. Second, the soil modulus K, which defines how stiff each spring is. Third, the number of springs, which determines how finely the beam is divided. More springs give more accurate result. Once these inputs are set, the code evenly divides the beam and assigns one spring per segment. At the two ends, the springs are assigned half the user stiffness to reflect realistic boundary conditions. The spring stiffness is applied per unit length, so the total reaction force at each spring depends on the segment width. The code uses the finite difference method to compute the structural response. It serves a system of linear equations derived from the beam spring model and output result in graphical forms. At the end of the process, the user can examine the structure behavior through clear plots of deflection, shear force, and moment across the entire beam length.
Hello, I'm Yuri Kim, and I'll be presenting the fourth part of our project, the analysis of two-column loads. This section models a continuous footing under two-column loads to calculate deflection, shear force, and moment, which are then visualized through graphs. I will explain the analysis process based on the 8-step flowchart introduced earlier. Let's begin with step 1, defining the design conditions. The 5 loads are calculated as a combination of dead and live loads, and the unit used is pound. The column centers are uniformly placed by dividing the beam into 6 equal segments. In step 2, the user provides input values. These include the flexure rigidity EI, the subgrade reaction modulus K, and the number of nodes N, which determines the precision of the analysis. Step 3 is discretization and spring assignment stage. The beam is evenly divided, and each node is assigned a spring representing soil support. At both ends, only half the spring stiffness is applied to reflect boundary effect. Step 4 is where we assemble the external load vector F. Each load is converted into a distributed load across its given width, and based on its center, the load is assigned to adjacent nodes. A loop is used to include all 5 loads into the force vector. In step 5, we build the stiffness matrix A and apply boundary conditions. Internal loads are treated using the fourth order finite difference scheme, and the beam ends are fixed with Dirichlet conditions, meaning deflection is 0 at both ends. Next, step 6 is normalization and conversion to a sparse matrix. This improves numerical stability and enhances computational efficiency using sparse matrix techniques. In step 7, we solve the system of equations and compute the results. We start by calculating the deflection, and from there derive the soil reaction, shear force, and finally the moment. Shear is obtained by accumulating the difference between reaction and load, and the moment is integral of shear. Finally, in step 8, we plot the results. You will see that shear force has discontinuities at load locations, moment reaches its peak between loads, and deflection is largest directly under the columns.
Now I will explain the 3-column load case. The code begins by accepting user input for key parameters. With the system set up, the program assembles the governing equations for a beam on an elastic foundation and solves for the deflection at each node. This yields the deflected shape of the continuous footing under 3 loads. After obtaining the deflection profile, the code calculates the internal shear forces and bending moments along the beam. These internal forces are derived from the deflection curve using beam theory relationships. Finally, the results are generated and plotted for visualization. This shows how the code structure facilitates calculating deflection, shear, and moment for the 3-column case, providing a clear understanding of the foundation's response under multiple loads. Now I will explain 5-column load case. The MATLAB code has been extended from the previous cases to accept 5 distinct load inputs and include them in the analysis. After same process, the program calculates the corresponding shear force and bending moment distributions. The shear force diagram clearly reflects the effect of each individual load. Notably, each concentrated column load produces a discontinuity, a sudden jump, in the shear force diagram. The magnitude of each jump is equal to the magnitude of the applied load. Between these jump points, the shear force varies linearly as expected in the spans between concentrated loads. This behavior confirms that the code correctly captures the shear force changes at each load position. The bending moment diagram would similarly integrate these effects, showing peaks under the loads. Overall, the 5-column case demonstrates the code's ability to handle multiple loads and how the structural response is visualized for a more complex loading scenario. This concludes our presentation on the Winkler foundation analysis for multiple column loads. Thank you for your attention.